Hi everyone, it's Sorkin. Today we are going to take a look at what is a stream processing and why do you need it. So let's first take an example. Let's take a very simple example of a fraud detection service. Let's say that let's first clarify the requirements for it. So let's say that we need to design a fraud detection service for a bank, and our requirements are we need to notify user if the amount of the transaction exceeds $1,000, or in other cases, we need to notify user if the sum of the transactions in 1 minute window exceed $2,000. So what would be the simple architecture for this scenario? So let's say that our user sends through the load balancer, it sends a request to a user service. So let's say that we are sending a JSON, which contains user ID, amount, timestamp, CD, and so on. So we are sending a user service microservice, and from the user service microservice, we are storing that to DB. Since it's a financial transaction, it's an asset transaction, so we are choosing RDBMS. So we are storing our transaction to the database, and at the same time, let's say fraudulent user also may make a request on behalf of our user. So we need to detect those cases and notify our user. So what we do is, we are storing our transactions to our table. So let's say that we have transaction ID, user ID, amount, and the timestamp. And also, how would our fraud detection logic would look like in this case? The fraud detection logic, in a very simple term, is if the amount is more than 1,000 and if the sum of all the transactions for the last 1 minute, if that more than 2,000, then in that case we are notifying a user. So for that we should run a query where we are taking all the transactions for last 1 minute for the particular user, and if that more than 1,000, then we are notifying a user. So for that we would have one more microservice, notification service, where we are sending which we are calling, and we are sending our user, and we are sending a total amount, which is, for example, in our case, 2,600, and the number of the transaction is 4. So which means that for this particular user with the ID 123, we received 4 transactions in last 1 minute, and the total sum is 2,600, and we are notifying a user. So we are calling a notification service microservice, and that microservice calls a user. So what's the problem with this architecture? The problem potentially might be this query that we are running. So let's just do a simple calculation. So for each transaction, let's say that each transaction that we receive, for example, this transaction, right? Let's say user ID and the amount, timestamp, and the CD, and the other fields. Approximately it's a 200. Let's take it as a 200 byte. So, and let's calculate how many transactions, how much storage do we need for 1 month. So our QPS is 5 kilobyte. And in 1 second, we are receiving 5,000 transactions, and the storage that we need for 1 month, 200 multiplied by 5K multiplied by 60 seconds multiplied by 60 minutes, 24 hours, and 30 days. It's a 2.6 terabytes. So approximately, let's take 3 terabyte of data, 3 terabyte of storage that we need for 1 month to store all our transactions. Which means that we are going to run our query, we will going to run after 1 month, we are going to run that on 3 terabyte of data. So what is the estimated query runtime? What's the estimated query runtime here? And to answer that question, let's first consider the factors that impact query runtime. The factors that impact query runtimes are first hardware, the specification of the server hosting our DB. So it's a CPU, it's a RAM, it's a disk speed, and etc. The next one is the DB config, the config parameters such as buffer pool size, query cache size, etc. And also concurrency control, how well our DB handles concurrent queries. And the next one, whether or not we are partitioning our tables, and also our tables and our DB, and how well our indexing is, and whether or not we are optimizing our query. Considering all that, so the total query time, we are going to take that the disk IO time plus whatever time we need for the CPU processing. For the disk IO time, assuming that each query generates 1000 IO operations due to index lookups and the data retrieval, and the average IO latency for, let's say in this case we are using NVMe SSD is around 0.1 millisecond per IO operation. So in that case, we are 1000 multiplying by 0.1, it gives us 100 millisecond, and the CPU processing time is 20. So total query time is 100 millisecond plus 20 gives us 120 millisecond. So 120 milliseconds, so you may say that, okay, so what's the big deal? 120 millisecond is not that high latency, it should be okay. But the problem is this solution is not scalable. The reason being is we are running this query only on 3 terabyte of data. Let's say after 2 months, our data increases to 6 terabyte, and at least we need 200 millisecond, which so our query runtime would be 200 millisecond. So our dependency is linear. The next one is that the increase in QPS. So today we are receiving 5K, tomorrow we may receive 10, 20, and so on. And the next one is that the adding joins. So here we are running a very simple query, but in reality, our query would be much more complicated. So for example, in this scenario, we need at least 2 tables, user table and the transaction table, because the one user can have many transactions. So dependency is one to many. So one user can have many transactions. And the next one, that the inefficient indexes. So as we grow our tables, so our also indexes may become inefficient. All this will affect our query runtime. So we cannot use this query to send a notification to a user. So what would be the other approach? What else we can solve this? How we can change this architecture to solve this problem? So the way we are going to do that, we are not going to read from our database. What we are going to do is, as soon as our transaction is stored to the database, as soon as it's stored, we are sending the copy of our transaction using tools such as Logstash or Kafka Connect. We are sending to a queue. So we can use Kafka here. So we are sending exact copy of our transaction to the Kafka. Why we are not doing that? Why we are doing that before storing that after storing to the database? Because before storing, if we send a copy to the Kafka, our transaction may not be successful. It may not be saved to the database. We need to send to Kafka only after the transaction is successfully completed. So our Logstash, either Kafka Connect, it monitors our database, and it sends the changes that for each row that we are adding to the table, it sends that to the Kafka. It sends that to the Kafka. From the Kafka, what we do is we are using one of the data processing engines. So for example, in this case, we are using Apache Spark. We are reading the data from the Kafka, and we are applying 1 minute window. We are aggregating the data, and those transactions that are fraudulent, potentially fraudulent, meaning that, for example, we have aggregated for user 1 to 3, and the amount is 2600. Number of the transactions are 4. So we are sending those transactions to a new topic in the queue in our Kafka. And what we do is, now our notification service and the user service, they are not connected. Our notification service is completely independent from the user service. It reads from the Kafka, and it sends those requests to a user. So it sends those requests to a user. So what has changed in this architecture? In this architecture, now we have 2 parts. First part, when we are saving transactions to the database, and the second one is the fraud detection service. These 2 parts are completely independent, so we can scale them independently. So for example, in the first case, if we are partitioning database, adding indexes, we don't have to think about twice how would that affect our fraud detection service, and vice versa. If, let's say, we are changing our fraud detection service, let's say we are adding some customized notifications. So let's say some user want to customize that if the amount of the transactions in last 5 minutes exceeds $10,000, so then in that case they want to receive the notification. So whatever the case is, so we are scaling this user service and the fraud detection service, notification service, we are scaling them independently. So let's just briefly take a look how Apache Spark works. So first we are doing for our case is we are defining a schema of the transaction JSON. It's basically the transaction, it's basically the JSON that we are receiving from the user. And the next one is that we are reading the transaction from Kafka and we are creating a data set based on that transaction. The next step that what we are doing is we are applying a 1 minute window and aggregate the amount for each user. So for example, let's say that we have, as we have seen the previous example, right? For user with the ID 1 to 3, we aggregate and we filter those transactions. We filter windows where the sum of the amount exceed 2,000, and we are sending those fraudulent notifications to Kafka. Fraudulent transactions, we are sending that to Kafka. What are the alternatives to the Apache Spark? So Apache Spark is one of the tools that we can use, and another data processing engines are Apache Storm. They are they are working almost similarly. So each of them, of course, have their own subtleties, but they pretty much work the same. So we have Apache Storm, Apache Kafka Streams, Flink, Samza, Apache Beam. And also if we talk about the cloud providers, so for example, Google Cloud GCP has the Google Cloud data flow, which is basically built on the top of the Apache Beam. And also other clouds have a services. For example, Amazon has the Amazon Elastic MapReduce or EMR, where you can easily spin up the Apache Spark or other data processing engines, and the same kind of service is provided by the Azure. It's the Azure HD Insight. So now let's take a look at what's the difference between the stream processing and the real-time processing. So the example that we have seen earlier with the fraud detection service, it's an example of the real-time processing. And the real-time processing and the stream processing, the difference between them are not that. So the difference between them, they are using the same tools. They are using the same big data technologies. The difference between them is arguably the volume of the data that we are receiving. The biggest difference between them is arguably the volume of the data. For the stream processing, we are receiving high amount of the request, high amount of the data. So our QPS is starting from 50K, 100K, and so on. For the real-time processing, the QPS is comparatively low, and because of that volume, our data flow in case of the stream processing, it's stream processing processes data in small or micro batches, where in the real-time processing, it processes each transaction separately. And for the latency wise, some latencies are low. It's either in microseconds to milliseconds. And in case of the stream processing, in the real-time processing, it's instantaneous response is expected, because, for example, the fraud detection service, right? We want to each transactions to be we want each transaction to be processed, and we want to give the user instantaneous response. And the complexity of the stream processing, because of the high volume of the data, is much higher. In case of the real-time processing, it's a moderate complexity. And because of the high volume, as I said, it's arguably the biggest difference between them. The consistency will be different. So in case of the stream processing, eventual consistency is expected. It's expected behavior. But in case of the real-time processing, we expect immediate consistency, because we need to notify the user as soon as we receive the transaction. So no delay should be there for the real-time processing. So what are the use cases? For example, for the stream processing, right? What is the use case for the stream processing? First one is social media analytics. For the social media platforms, they handle millions of user notifications, including likes, comments, and shares, to analyze trends and show relevant ads. The next one is that, for example, IoT sensor data, right? For example, factories, or let's say that the smart homes, smart cities, they use stream processing to analyze the data from the connected devices. For example, let's say that the temperature sensors or traffic sensors, and adjust operations based on that incoming data. So the next one is, for example, real-time log analysis. So for most of the tools in the cloud infrastructures, they are generating logs. For example, let's say that the AWS CloudWatch, or let's say that the Elastic Stack. So we are using stream processing to analyze the logs continuously, and for the errors, let's say that, or for the performance bottlenecks and the similar kind of issues. And the next one is that the real-time marketing. So for the real-time marketing, for example, let's say that the e-commerce, right? For the e-commerce websites, we use that to analyze the user behavior, clicks, and interactions in almost real time, and we are near real time, and we show the personalized product recommendations and the offers. So how about the real-time processing? For the real-time processing, we have seen one example earlier, right? Fraud detection service. But what are the other cases? The one is that, for example, high frequency trading, HFT systems. So for example, for the, let's say, stock markets, they use real-time processing to execute trades based on the incoming market data with very low latency. The expected latency should be low. The next one is, for example, air traffic control systems. For these systems, we should process data from the radars, and we need to process the data from the other sources in real time for the safe operation of the aircraft. And the next one is medical monitoring devices. For these systems, we track vital signs, such as, for example, let's say that the heart rate, blood pressure, and process the data in the real time. And the last one is the autonomous vehicles. For the autonomous vehicles or the self-driving cars, we rely on the real-time processing of sensors to make immediate driving decisions. So again, in all of these cases, for the real time, we need to our response should be our process of the data should be instantaneous. While with the stream processing assumes that we have unlimited incoming number of the data, so that data might be starting from the QPS might start from the 50K for 100K, and some delay is expected, so it's eventual consistency there. Okay, that's it for today. Hope you like my content. If you like it, please hit the like button and subscribe my channel. See you next time. Bye.